In this video, we're going to start our journey on integration. We're going to look specifically at antiderivatives and basic indefinite integration. Now, integration, simply put, is the inverse operation of differentiation. In later videos, we're going to look at how to actually visualize it and picture what an integral is. But we're just going to start off by looking at its connection with derivatives and the fact that it's an inverse operation. In the next video, we'll explore some examples. So this is more the theoretical video. So let's have a look at the following functions. Let's start with y equals 3x squared. If I want to differentiate that function, remember the 2 comes to the front, I times it by the 3, and then I subtract 1 from that 2, and I land up with my derivative being 6x. Great. Let's have a look at another function, the function 3x squared plus 2. Again, if I differentiate 3x squared, I get 6x, and the derivative of 2 is 0. Right, one more. If I look at the function 3x squared minus 10, again, the derivative of 3x squared is 6x, and the derivative of negative 10, which is just a constant, is 0. Now, what you should have noticed that each of these original functions was different, but they had exactly the same derivative because the derivative of these constants is just 0. Now we're going to turn it around and we're going to look at these guys here as the original function. So that's why I'm just saying they're the function f. And I want to go backwards. So if I'm given my original function, I want to know, if I'm given basically the derivative, I want to know what is the original function. Now we call these guys the derivatives. They're just our original functions, but when we go backwards, we call these functions the antiderivatives. And here we're going to represent them with a capital F. So let's have a look at the definition of antiderivative. So a function f, like these guys here, is an antiderivative of f. Let's just explore that, why I didn't say the antiderivative. Now, if you look at these functions here, they could lead to 3 different antiderivatives. So the antiderivative is not unique. So I can't talk about the antiderivative, I just need to talk about an antiderivative. So let's try again. A function f is an antiderivative of f on an interval I. Don't worry about that too much. Just bearing in mind functions might not be differentiable or integrable everywhere. If we differentiate that function, like if we differentiate one of these guys, and we get our function f for all of our x on the interval that we were given. Okay, so let's have a look here. The antiderivative, and I actually probably should have put an antiderivative, or I'll show you now why I actually wrote the antiderivative of the function 6x is 3x squared plus a constant. So here we had 3x squared plus 0, here we had 3x squared plus 2, here we had 3x squared plus negative 10. So by saying plus c, we are talking about the family of all the antiderivatives. And when we actually find antiderivatives, we must put that plus c, because we don't know what constant could be in that place. Okay, so that's just the general representation and some of the notation we use. Let's delve a little bit more into our notation. What notation do we use for antiderivatives? Now, I'm going to go a little bit into the background of the dy over dx, but I'm not explaining all the details. Those will be explained in a later video when we can actually represent integrals as the area under a curve. So just simply put, if I've got dy over dx, derivative of y with respect to x being a function, then I can almost think of timesing both sides by dx. It's actually just a really incremental amount. Don't get too hung up on that. Like I said, I'll explain this a little bit more when we've learned to visualize integrals. So basically, we're thinking of timesing both sides by dx, and we end up with dy equals f of x dx. But now, what is y if dy is equal to f of x dx? Or simply put, y here, y is the integral of the function. So let's just explore this notation, that funny sign that you've never seen before. That's kind of like a stretched out S and is linked very close to sum, which we'll see again in later videos when we really explore what an integral is and how to visualize it. But that is the sign for integration. Find the integral of the function, which we call the integrand, and this is called the variable of integration. The easiest way to look at it is it's showing you what you must integrate that function with respect to. Just like when we differentiate a function, this is saying differentiate y with respect to x. X is the variable. This is saying integrate f with respect to x. We land up with a function plus c, which is called our constant of integration. So this is the notation you will be seeing. Let's see how we read this guy here. So integral f of x dx is read the antiderivative of f with respect to x. So I'm looking, if this is actually my derivative, what is the original function? Remember that original function is the antiderivative. The operation of determining an antiderivative is called antidifferentiation. In other words, the opposite, the inverse operation to differentiation, or indefinite integration. So an antiderivative can also be called an indefinite integral. That's another name for it. Now let's have a look at some of our rules of integration, or our rules of finding the antiderivative. And they go hand in hand with our differentiation rules that we already know. So let's start with the basic one. If I differentiate the derivative of a constant, in this case with respect to x, but remember this can actually be any variable. It can be t, it can be delta, it can be theta. Here we're just working with x, just for simplicity's sake. So the derivative of a constant is 0. So remember, integration is the inverse operation. It goes the other way around. So if I want the integral of 0, again, don't forget your dx is equal to constant. When we go backwards, so I start by 0, I go to the constant. Let's try another one. A derivative of a constant times x is just equal to the constant. For example, the derivative of 5x is 5. Go the other way around. So the integral of a constant is equal to the constant times x plus our constant of integration. All right, let's try another one. The derivative of a constant times a function. Remember, with differentiation rules, we can just take the constant out and just differentiate the function. Very similar for integration. The integral of a constant times a function with respect to x, we can just take that constant out and integrate the function. Here, the derivative of a sum is the sum of the derivatives, so we can differentiate each function. Same goes for difference. Same rule applies to integration. The integral of the sum of the difference is the sum of the difference of the integrals. Integrate each separately and then add them or subtract them. Now here's one of our most important rules, which we learned in differentiation, which translates into integration, is the power rule. The derivative of a power is equal to, now remember, you take the exponent to the front and you subtract 1. Now, it works opposite way around with integration, and this will be a lot easier to actually visualize when we're doing examples. With the integral of a power, we now, instead of subtracting 1, we add 1, and we divide by the exponent. That's just to take away the exponent that ends up coming to the front. We want to take it away. And we add our constant of integration. Just remember that your denominator cannot be 0, so your n cannot be -1. Here's an extension of our power rule to a linear function, and again we'll extend it further to functions that aren't linear in future videos. But the derivative of a linear function where the base, the derivative of a power where the base is a linear function, we use the chain rule. n comes to the front, we keep the base as the whole function, we subtract 1, then we go inside the brackets and we differentiate that, and because it's linear, the derivative of ax is just a. So when we're doing the integral of a power where the base is a linear function, let's actually start here. Again, we add 1 and we divide by the exponent, but then we also times by 1 over a, and that's just to get rid of that a. Don't forget to add your constant of integration. I would print these rules out or write them down, keep them next to you. We're going to use them in the next video when we explore some examples.